The generative AI era represents a new phase in the history of artificial intelligence. Rather than focusing solely on prediction or classification, AI systems now generate text, images, code, and other content. This shift reflects deeper changes in architecture, scale, and deployment. Earlier AI systems primarily recognized patterns or selected predefined outputs. Generative AI systems go further by producing novel content. This does not mean creativity in a human sense, but statistical generation based on learned patterns from large data sets. Generative AI refers to models that learn the underlying structure of data and sample from it to create new outputs. These outputs are not retrieved from a database, but synthesized dynamically, making each response potentially unique. Historically, most AI applications were reactive. They responded to inputs by selecting labels or scores. Generative systems instead construct outputs token by token, enabling flexible responses across many contexts. What distinguishes this era is not a single invention, but a convergence of factors. Architecture, data scale, and infrastructure aligned in a way that enabled generative models to perform reliably at scale. Deep learning provided the foundation. Neural networks capable of learning high-dimensional representations made it possible to model complex data distributions across text, images, and audio. The transformer architecture was a turning point. Unlike earlier sequence models, transformers process inputs in parallel and rely on attention mechanisms to model relationships efficiently. Transformers use attention to determine which parts of an input are most relevant when generating each output element. This design enables efficient handling of long sequences and complex dependencies. Attention allows models to dynamically focus on context. Rather than processing information sequentially, transformers evaluate relationships across the entire input at once. This efficiency made it feasible to train very large models. Longer context windows and richer representations became practical, improving coherence and relevance in generated outputs. Language played a central role in this shift. Text data is abundant, diverse, and expressive, making it an ideal training medium for large generative models. Large language models emerged by scaling both data and parameters. Increasing model size consistently improved performance across a wide range of tasks. Model parameters represent learned relationships. As parameter counts grew, models gained greater expressive capacity, allowing them to capture more nuanced patterns in data. Pre-training became the dominant paradigm. Models learn general language patterns through self-supervised objectives before being adapted to specific tasks. Fine-tuning allows pre-trained models to specialize. This separation enables reuse of general knowledge while adapting behavior for particular applications. Generative models became general-purpose tools. A single model could perform translation, summarization, question answering, and more without task-specific redesign. Generative AI expanded beyond text. Models now generate images, audio, video, and code using similar underlying principles. Multimodal systems integrate multiple data types within a single model. This enables richer interactions and broader applicability across domains. Importantly, generative AI produces new content rather than retrieving stored examples. Outputs are statistical constructions based on training data distributions. Despite impressive outputs, generative models do not understand meaning. They generate based on patterns, not intent, awareness, or reasoning. Outputs often appear intelligent because they are fluent and contextually appropriate. This fluency can be mistaken for understanding. Natural language interfaces lowered barriers to use. People can interact with AI systems conversationally without technical expertise. This shift changed user experience. AI systems began to feel more like assistants than tools, increasing adoption and experimentation. Public exposure to AI expanded rapidly. Generative systems reached mainstream users, unlike earlier AI technologies that remained largely invisible. Access to generative AI became widespread. Cloud platforms and APIs enabled organizations and individuals to integrate AI into workflows quickly. Economically, Generative AI supports productivity. It assists with drafting, coding, summarizing, and analysis rather than replacing entire roles outright. Industries such as media, education, and software development experienced rapid experimentation. Generative tools altered how content and code are produced. The speed of adoption exceeded prior AI waves. Network effects and ease of integration accelerated diffusion across sectors. Cloud infrastructure enabled this scale. Centralized compute and standardized interfaces allowed models to be deployed globally. AI increasingly functions as a platform service. Models are embedded into applications rather than delivered as standalone products. New risks accompany these capabilities. Generative systems can produce incorrect information confidently, creating challenges for trust and reliability. Because outputs appear authoritative, users may over-rely on them. Managing uncertainty and error becomes essential. Biases present in training data can be reflected and amplified in outputs. This raises fairness and representation concerns at scale. Generative AI also raises intellectual property questions. Training data sources and output ownership remain contested. Training large models is resource-intensive. Energy use and cost create sustainability and access challenges. Control over advanced models is concentrated among organizations with significant resources. This raises questions about power and governance. Regulatory frameworks struggle to keep pace. Deployment often outpaces oversight, creating gaps in accountability. Public discussion sometimes conflates generative AI with general intelligence. This confusion fuels unrealistic expectations and fear. Generative AI remains narrow. It performs tasks within learned domains and lacks autonomy or general reasoning. Media attention amplified this wave. Visible outputs and conversational interfaces made AI feel suddenly present. Structurally, this era differs from earlier AI cycles. Progress is continuous, driven by scaling rather than isolated breakthroughs. Unlike past waves, generative AI delivers sustained value across many domains, supporting long-term adoption. Its endurance reflects real utility. Organizations continue investing because benefits are measurable and repeatable. Generative AI is becoming infrastructure. It is embedded into everyday tools and workflows. Long-term implications extend to work, education, and knowledge production. These changes will unfold gradually rather than instantly. Generative AI functions as a general-purpose technology, affecting many industries simultaneously. Despite its impact, limits remain. These systems lack understanding, agency, and intent. History reminds us that expectations must be managed. Capability does not equal intelligence. This era completes the historical arc from symbolic rules to data-driven generation. Next, we move from history to foundations by examining core AI concepts that explain how these systems actually work.